This is the last part of a series on optimizers. In this video, we will take a look at the Adadelta and Adam optimizers. This video was produced in Korean and translated into English. My voice was generated by AI, text-to-speech. The stochastic gradient descent SGD is the most basic optimizer. Momentum optimizer and nag optimizer add momentum to SGD. And the Adagrad, RMSprop, and Adadelta optimizers adjust the learning rate according to the gradient history for each parameter. Finally, Adam combines momentum and adaptive optimizers to take advantage of the best of both optimizers. In this video, we will take a look at the Adadelta and Adam optimizers. Let's then compare the paths each optimizer takes to reach the goal on a simple loss surface. First, let's look at the Adadelta optimizer. Adadelta is an optimizer proposed by Matthew Zeiler in this paper in 2012. Let's take a brief look at Chapter 3 of the paper. The author of the paper points out two problems with Adagrad. The first problem is the continual decay of learning rates throughout training. And the second problem is that a manually selected global learning rate is required. This problem exists not only with Adagrad, but also with other optimizers. To solve these issues, this paper presents two ideas. We'll look at this in more detail on the next page. Let's look at the first idea presented in the paper. The Adagrad optimizer seen in the previous video is as follows. G in the denominator accumulates the squared gradients from each iteration starting at the beginning of training. In this formula, since each term is positive, this accumulated sum continues to grow throughout training, effectively shrinking the learning rate on each dimension, W. After many iterations, this learning rate will become infinitesimally small. Let's call the gradient of LG. When a time series of G square is like this for iteration T, all past G squares are accumulated in G. The time series of G increases monotonically like this. Then the learning rate continues to decrease. The idea 1 presented in the paper is as follows. Instead of accumulating the sum of squared gradients over all time, we restrict the window of past gradients that are accumulated to be some fixed size t. That is, we accumulate the squares of the gradient over this time window. With this windowed accumulation, the denominator of Adagrad cannot accumulate to infinity and instead becomes a local estimate using recent gradients. This ensures that learning continues to make progress even after many iterations of updates have been done. Since storing t previous squared gradients is inefficient, our methods implements this accumulation as an exponentially decaying average of the squared gradients. In other words, G is calculated as the exponential moving average of the squared gradient like this. In fact, this is the RMSprop optimizer that we already looked at in the previous video. RMSprop was not published as a paper, but was mentioned by Jeffrey Hinton in his Coursera lecture. The author of this paper probably thought the same thing at the time. Next, let's look at the second idea presented in the paper. This is to match the units in the formula for updating parameters. When considering the parameter updates, delta W being applied to W, the units should match. That is, if the parameter had some hypothetical units, the changes to the parameter should be changes in those units as well. When considering SGD momentum or Adagrad, we can see that this is not the case. If W has units in meters, then delta W must also have units in meters. If the units of delta W are kilograms, then adding kilograms to meters makes no sense. For SGD or momentum, the formula for updating parameters is like this. Assuming that the loss function L and the learning rate alpha are unitless, the units of delta W are the units of the gradient of L, which is the reciprocal of the units of W. The units of W and delta W do not match. For Adagrad, the units of G are the units of the squared gradient of L, which is the reciprocal of the units of W squared, 4. Therefore, the units of this part are the units of W, and delta W has no units. In contrast, second-order methods, such as Newton's method, that use Hessian information or an approximation to the Hessian, do have the correct units for the parameter updates. That is, the units of delta W are the same as those of W. Noticing this mismatch of units, we considered terms to add to equation 10 in order for the units of the update to match the units of the parameters. Since second-order methods are correct, we rearrange Newton's method, assuming a diagonal Hessian, for the inverse of the second derivative to determine the quantities involved as follows. Since the RMS of the previous gradients is already represented in the denominator in equation 10, we considered a measure of the delta W quantity in the numerator. If the diagonal Hessian for W1 and W2 is like this, then its inverse matrix is like this. So this is the inverse of Hessian. And applying the idea 1, we use the RMS value of the numerator and denominator. And if we replace the inverse Hessian of this equation with this expression, we get the equation 14. Delta WT for the current time step is not known. So we assume the curvature is locally smooth and approximate delta WT. By compute the exponentially decaying RMS over a window of size t of previous delta W to give the Adadelta method as follows. That is, instead of RMS delta WT, we use RMS delta WT minus 1. When the delta W squared time series is like this, we use the previous exponential moving average value as an approximation instead of the delta WT value. The exponential moving average of delta W squared is denoted by S. Then RMS delta WT minus 1 can be calculated as follows. And the parameter W can be updated in this way. Epsilon is a small constant value to prevent this value from becoming 0. You can see that there is no global learning rate alpha in this formula. Therefore, Adadelta does not require you to specify a global learning rate alpha. However, TensorFlow and PyTorch use the global learning rate alpha. They additionally apply alpha in the formula for updating W. Setting alpha to 1.0 behaves the same way as in this paper. This is the Adadelta optimizer. Now let's see how Adadelta works through a simple example. The formula for the Adadelta optimizer can be summarized as follows. Let's use this loss function used in the previous video. The gradients of the loss function L with respect to W1 and W2 are as follows. And let's say the starting point is 2, 3. Then the gradients with respect to W1 and W2 at the starting point are -4 and +2. Let's set the rho to 0.9. If rho is set to a large value, G and S will change gently. But if rho is set to a small value, G and S will change significantly and the path may become unstable. First, let's calculate G using this formula. The vector G for W1 and W2 is 1.6, 0.4. Next, calculate S using this formula. The initial values of S and delta W are both 0. Then S of W1 and W2 are both 0. Next, we update each W with this formula. I set the epsilon to 10 to the power of -4. The initial value of W1 is 2 and G is 1.6. So W1 is updated to 2.03. The initial value of W2 is 3 and G is 0.4. So W2 is updated to 2.968. Let's update W one more time. The gradients at this point are as follows. And at this point, we recalculate G and S. The previous G vector was 1.6, 0.4. And the square of the current gradients are like this. Then the GT plus 1 for W1 and W2 are 2.99 and 0.735. Previous S is still 0, and delta W1 is 2 minus 2.03. And delta W2 is 3 minus 2.968. Therefore, S for W1 and W2 becomes as follows. Updating W1 and W2 using G and S gives 2.061 and 2.93. In the figure on the left, W moves from this point to this point and then to this point. The path looks like this, but it's so small that it's hard to see. For other optimizers, we set the global learning rate large enough to make the path visible. However, because Adadelta does not specify a global learning rate, the path moves little by little and is not clearly visible. In this case, the initial global learning rate corresponds to around 0.01. Adadelta works this way. Next, let's use TensorFlow to check the path W takes in this example. We use the loss function used in the previous example. And we will use the Adadelta optimizer provided by TensorFlow. The starting point of W is 2, 3. And the target point is 4, 2. Create a TensorFlow variable for parameter W. The initial value is W0, the starting point. And we create an Adadelta optimizer. Rho is set to 0.9, and epsilon is set to 10 to the power of -4. And as mentioned earlier, Adadelta does not require you to specify a learning rate. However, TensorFlow uses this formula to update parameters, so you can additionally specify the learning rate alpha. If you specify a learning rate of 1.0, it behaves the same as Adadelta in the original paper. Here we set the learning rate to 1.0. Next, we perform automatic differentiation, as we did in the previous video, to find the gradient of the loss function L with respect to W. Then we update each parameter using this gradient. Parameter records are stored in a list to observe changes in parameters. Repeat this process 10 times. Finally, print the parameter history. The results are as follows. has been updated 10 times. W is a little closer to the target point 4,2. These results agree well with the hand calculations on the previous page. Let's run this code. The results are as follows. Next, let's look at the adaptive moment estimation optimizer. It is simply called Adam. Adam was proposed by Kingma and Ba in 2014 and is a combination of adaptive optimizer and momentum optimizer. Adam takes advantage of the best of both optimizers. The formulas for the Adam optimizer are as follows. G is the gradient of the loss function L with respect to W, and M is the momentum factor. The momentum component is obtained from the exponential moving average of the gradient. In the momentum optimizer, the momentum vector was calculated as follows. In the Adam optimizer, it is calculated the exponential moving average using 1 minus beta instead of learning rate alpha. We then calculate G as the exponential moving average of the gradient squares, as we did in RMSprop and Adadelta. Then we update W using M and G. However, in Adam, M and G are used modified. Again, M and G are exponential moving averages. And the initial M and G values are both 0. For example, let's say the G or G squared time series looks like this. Then the exponential moving average will look like this. It starts at 0 and becomes similar to a standard moving average over time. That is, it initially does not properly reflect the average of the time series. The ones that correct this are M hat and G hat. Consider the beta to the power of t in the denominator. Let's say the beta is set to 0.9. At the beginning of the iteration, t is small. For example, if t is 1, the denominator 1 minus beta will be 0.1. Then M hat becomes 10 times larger than M. As t increases in the latter part of the iteration, the beta to the power of t approaches 0. Then M hat becomes similar to M. That is, M is modified significantly at the beginning of the iteration and modified slightly toward the end of the iteration. This is a bias-corrected estimate. The same goes for G hat. This is the Adam optimizer. Algorithm 1 on the right is the Adam algorithm presented in the paper. This is identical to the formula on the left. Lastly, let's compare the paths to the target point for each optimizer. This code is a compilation of all the codes we have used previously. The global learning rate was set high so that the paths were clearly visible. In the case of Adadelta, since it does not use a global learning rate, the path is not clearly visible, so we set it large. The rest of the code is the same as the code we looked at earlier. Let's take a look at the results. If you set the global learning rate large, you can see this zigzag oscillation in the stochastic gradient descent optimizer. The momentum optimizer dampens oscillations, while other optimizers gradually find the target point as follows. The path depends on the shape of the loss surface and the hyperparameter settings. Let's run this code. The results are as follows. So far, we have looked at the optimizer through a total of 3 videos.